Hello, everybody. This is Professor Ma, and this is the summary on the computational techniques for Maclaurin expansions. Of course, for Taylor expansion also, just a little bit more complicated notations. Uh, Let me start out with a reminder that we did the Maclaurin series, which is given by this formula right here, where f of x is, you can differentiate infinite many times. And in particular, it's Mach series because this formula is we're plugging in x equal to 0. So this is about derivative around x equal to 0. Therefore, this is an expansion around the point x equal to 0. And the following are the max expansion. Okay, for polynomial, you get back the polynomial. And for exponential functions, you get this and sine, cosine, 1 over x, etc., etc., and his log x plus 1. Okay. So these are the max expansion which we can calculate directly using the expansion formulas. Now, how do we compute in general a formula, elementary formula? Suppose sine, cosine involve various functions of these three families. How do we find the Mach series for that? Well, just like taking derivatives, okay, and we're going to build. We theoretically, I mean, the computation, of course, is messy, that we can find the Maclaurin expansions for any elementary functions because of the following reasons. Okay, we have two Mach expansion of two functions. Okay, f(x) and g of x respectively, and then the Mach expansions of the respects some difference, products and divisions. That means you get the Mach expansion, you get the Mach expansion of the sum of the difference of the product of the quotient. Okay, and so also respect composition. If you take one of the formula, plugging another formula, yeah, absolutely. Okay, you get a polynomial expansions. That's the Mach expansion of the compositions. So here are some examples of it. So we are going to go back to the formula over here, and if you don't remember the formula, go back to this page, and then you can look at it. Okay, check it. Mach expansion of sine x plus cosine x. Well, here's the Mach expansion of the sine x, and here's the Mach expansion of the cosine x. Notice the sine x covers the r powers, cosines are even functions, cover all the even powers. If I add them together, then I get this series of cosine x plus sine x. Okay, which is the reason this is true is because if I were to take the derivative, keep taking derivatives of the sum, I could take derivative of the individual one. So I will get the expansion of the individual one, the sine, one for the cosine. Okay, so that's why it's kind of obvious in this sense. And by playing around with the in the index, I can actually write this as a sum of two indices. And if you want, we can put them into various form. Okay. So in this case, I just wrote down the individual summation notation for the two of them. And here's a Mach series of x squared and ex, and the Mach expansion of x squared is itself. The Mach expansion of e to the x is these summations. And so take x squared times that. And so then we have the max expansions of the product. If you want to put the x squared into it, that I can write as a summation, infinite sum, in such a manner. Okay, so this just play around with index, and here, sine x squared. Mac expansions respect compositions. So if I were to expand sine of x, this is the expansion formula for sine of x. So the way to view this is I can view that sine expansion of sine of u is u here, u here, u here, and u, like in the chain rule in back, u can be any formula in x. Okay. In particular, if it's x squared, then all I have to do is stick u in there as x squared, and then stick x squared in for u, and that will give me the expansions. Okay. And that's true for any formulas in x. And this is in the closed form. And for fractional formula, such is actually kind of interesting. So here is a max series expansion. There are various ways of expanding these. One of the more basic way is just do long divisions. Okay, and if you remember how we carry out long division, we line things up. In this case, we're going to line up from small to large degree. So inside is x, outside is 1 plus x squared. Okay, again, the small ones out here. So I can end the quotients. 1 multiply 1 give you x, so x times 1 is x. The x times x squared is what? Plus x cubed. Okay. And subtract. I'll quite that I'll get minus x cubed. Then divide again. 1 multiply to 1 give me x cubed. Well, it's minus x cubed. And multiply minus x cubed minus x to the fifth. Okay, subtract. Cancel. This is the x to the positive fifth. And then you enter the quotient again, is going to plus x to the fifth. And by this, you can probably see the pattern. Okay, so this is one way to do it. So you can do this for every polynomial, p of x divided by q of x, okay? And you put p of x and q of x as such, just like long division, but remember, put the large degree to the back, and the numbers in the front, then start the division. So this is actually one way to extract the Maclaurin series, but this is by using the formulas. Okay, you have the formula 1 over, again, this you can treat it as a u, so 1 over 1 minus u is 1 plus u squared, blah, 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 is such infinite sum of u to the kth power. Now I'm going to replace, notice has to be a minus sign here with the formula. So in this case, I have to replace a plus by a minus sign, meaning the u is negative x squared, okay? So be a little careful with reading the sign when you use this formula 1 over 1 minus x. Okay. And so this is the infinite sum for 1 over x plus squares, and then multiplied by x, remember? That's how we get the ones that we did. Remember what we did with the long division? Okay, x cubed, max fifth, and so on and so on. Okay, so that's what this is. And okay, that's it. That's basically how we can calculate max series using the known expansions. Okay. It's not easy, because the more you want to calculate toward the back, of the larger degree of the Mac expansions, the more complicated it gets in general. Okay, that's it. Bye bye.